All right, cool. So, hey everyone, my name is Dan. I'm an engineering officer, and today I'm going to be presenting about hardware hacking. Yeah, I guess with that, I will get started. So I always first start off with my little spiel that digital electronics are actually a lie, and that we don't work in this idealized world where everything is actually a zero or a one, because it's not. So the way that computers actually work is they are able to differentiate between two states. And that's why you hear people say, well, when you're using a computer, everything's in binary. And the two states that it can detect are voltage or no voltage. And every chip will have its own specifications for what a cutoff voltage is. And all that means is that it's a way to determine if a voltage is considered a 0 or a 1. And usually somewhere in the middle is just considered undefined, and no one really knows what will happen. And this is kind of the basis of especially lower level hardware hacking, because since it's just a voltage and not like an idealized 0 or 1 that we learn to work with, we can actually change that and cause unexpected behavior that the software doesn't expect from the hardware and take advantage of issues there. Cool. So next slide is how we think of hardware in terms of security. So there's a lot of devices that people like to get their hands on. The first two would be IoT and embedded systems. And for those that don't know, IoT stands for Internet of Things, and is kind of a type of embedded systems. But generally, IoT is restricted to routers and just various smart gadgets that connect to the internet that are laying around your house. Embedded systems are generally more serious. So it's a wider term, but they can be used to describe things that might have a more serious thing that it needs to do. So like, for example, an ATM is considered an embedded system, or like your car's ECU, which controls how the car basically does everything now. And another example would be like, flight controlling software that works with the hardware that actually controls the plane. And all of those are embedded systems, and actually are pretty interesting when looked at from a security perspective. And the last two are game consoles and personal computers. Personal computers have definitely a smaller attack surface that people are worried about as far as hardware goes, because generally once someone has your hardware, there's not much you can do to stop them. However, I do have an example that I'm going to talk about later on in the slides on some hardware attacks against personal computers. And lastly, we have game consoles, which are kind of some of my personal favorites to talk about, because they're always kind of a closed lockdown system that no one really knows how they work until they've been reverse engineered. And a lot of times the only way to break into these systems, because their software is like really, really well hardened, is to use basically hardware attacks to trick the software into thinking something's happening that isn't actually happening. And yeah, so I'll first explain here the classes, I would say, of hardware exploits. And a lot of the more basic ones are actually what I would like to call just code execution as a feature. So imagine that you had like a software program that just takes like shell code or system commands and lets you do whatever you want. Now, technically in hardware, there's actually a lot of stuff, especially in IoT and embedded systems, that basically already has this. So if you take the hardware apart and you know what to look for, you can usually get access to a debug interface that will let you do whatever you want and is not actually locked out properly. And that is usually because, I mean, the debug interfaces are there for a reason, and the actual developers of the product needed that to make sure that their product worked after it was released to production. And that can leave some interesting avenues to explore. And two more like technical attacks that take more advantage of the digital electronics thing is glitching attacks and memory attacks. So whenever you have access to a computer's memory, it's pretty much game over, because if you can read or write to whatever the computer is doing, especially with personal computers, you could just change the operating system kernel or modify it to your will. And bypass login screens or copy secrets and whatever. And glitching attacks are far more commonly used in game consoles and hardened devices that may not have exposed debug interfaces that trick the CPU by, pulling, by slowing the CPU down or resetting the CPU at a weird time or disrupting the communication of the CPU with the rest of the hardware at a certain time that causes the software to read something incorrectly and mark something as verified even when it's not. Yeah, so I'm going to go over some debug interfaces that you might see when you're reverse engineering a device, or just common interfaces that are used with hardware. So the biggest thing here is that computer, especially embedded systems, have many components that have to communicate with each other. And that led to the creation of these protocols, which are mostly serial now, that are used to send bytes between different devices and peripherals on computers. So the first one would be JTAG. JTAG is not actually used for communication. So JTAG is usually just used for debugging hardware. And what it allows you to do is basically, it's like a daisy chain connection of all of the data buses of other chips that are on your board. And what that means is that you can essentially send whatever data you want to certain lines on chips that have been hooked up to this JTAG port. So if you find a JTAG port, usually you can actually just straight up start debugging the CPU, like if you were using GDB or something, and that's obviously code execution. The next one I want to talk about is UART, which basically is similar to the other communication protocols below, but is unique in the fact that it is also used for debugging, and that it doesn't require a clock to synchronize data. It just needs to either have some smart initialization code that synchronizes it, or it needs to start at the same time as the other thing, and then will continually sending and receiving bits at the same rate so that it never goes out of sync. So UART usually is either a communication or debug port. Whenever it's used as a debug port, it's usually more common in embedded devices that are running Linux. And it's used basically to just give you a Linux shell over UART the same way as if you would SSH into a computer. And the next one is I2C, which is a serialized way of, it does require a clock of sending data. Same thing with SPI. And a more interesting one that we'll talk about later is called DMA. And it's used when you need to send fast transfers. So let's say you have a graphics card on your computer and that connects using PCI Express, which requires DMA to function properly just because it needs to be sending stuff really quickly. So SPI, I2C, and UART are actually pretty slow in comparison to DMA, which is not super limited by the protocol of how fast it can go. So this is just an example of what UART would look like. As see how they show logic 1s and logic 0s. It's because actually, if you were looking at that on an oscilloscope, which shows you voltage over time, it would literally just be the signaling level, which would be usually 3.3 or 5 volts, or 0. That's what you would see, and it would look exactly like this. But yeah, this is just kind of an example of what one of these things would look like on an oscilloscope. So the thing about these is, in the software, it's harder to actually glitch the protocols themselves out, because usually embedded systems have hardware support for these, which means that all the programmer needs to do is pull some sort of register or continually check a register, or tell the hardware to actually interrupt the software whenever it has data for it. And that makes it so that if you get access to any one of these protocols, you might actually be able to do something to the device or hijack it. And generally, on especially lower end embedded devices like routers, you're going to basically always find a UART shell that may or may not be protected. A lot of times it's not. And I guarantee you that some of you that are here today, like if your router at home, if you took it apart, you could identify UART pins really easily and just get a root shell on like basically what is a Linux computer that happens to route all your internet traffic. And yeah, so this is what I mean by embedded devices need to communicate. So this is how like the inside of a router, and what it's showing is that all of these different things are connected back to the main CPU there on like invisible traces that go through that are layered in the PCB. And if you are able to see there's actually UART listed right here. That's what UART would look like. And generally on something like this, they're running Linux, which means you can just connect to that and get a root shell. And that's what this is demonstrating. And the thing about this is it's actually a lot easier than you would expect, because there are USB devices that you can just plug into the side of your laptop, and then that have like 4 pins that will just plug into those headers right there and get you a Linux shell on your embedded device. So the next thing I'm going to talk about is glitching attacks. And these are super cool because they abuse the fact that, like I said earlier, digital electronics don't exist, even though they do, but not on that idealized model. And it's, like I said, just changing the voltage of some hardware so that software gets confused. And I'm gonna kind of go into detail for each of these 3 things that are kind of like case studies that I think are really interesting. So the first one that I'll talk about is the 360. The Xbox 360 has an RGH. It has this thing called RGH, which stands for Reset Glitch Hack, which basically gives you unsigned code execution. And the Wii has this thing called that researchers use called the Tweezer attack, which I will explain. And lastly, let's say you do have an embedded system, so like some IoT device that was secured a little better, where they disabled the UARTs or something, or the JTAGs in software instead of hardware. You can actually disrupt the communications later on so that it gets confused and just gives you access anyway. But yeah, so but before we like dig into the more serious examples of those, and I like try to explain them a little bit, I need to talk about some like circuit knowledge, just so that you guys will have like at least some reference point. So for basic resistive circuits, we have V equals IR, and voltage, what is that translates to voltage is equal to current, which is I times resistance. And resistance is just basically a way to dissipate energy in the form of heat. Usually a resistor will just like burn a little bit. And this active circuits are more complicated, but for DC stuff, which is mostly what we're doing, it's not super important for this. But anyway, so what happens if you short 2 lines together? And I know a lot of people are going to say, well, if you short 2 lines together, you're going to get like burned electronics. It's going to be a nightmare, because whenever you hear someone say the word short, you probably think of, like a big black spot on some broken piece of electronics. However, with electrical engineering, that's not actually what that term means. When you short 2 lines together, all that means is that you're connecting them without that resistance. And the only time you're going to burn stuff is when you short a power to ground, which basically means that you are causing infinite current, which infinite current is just like electrons moving in the wire to go to the wrong spot. And that is what causes stuff to like explode, burn, whatever. So what we can do here with this is short 2 lines together, and they would then become in parallel, which means that their voltages are the same. And an idea here is that, yeah, and the idea here is that when we short 2 pins together on a flash chip, we can cause read errors. And generally with some of these embedded devices, if you're able to do that early on in the boot process and they're locked down really well, they may have forgotten to check their failure paths. And that is what pin to pwn stands for. So basically the idea behind this attack, you short 2 pins, specifically like an address pin or a data pin together, so that they're not really carrying any power. It's just signaling mostly. And once you have them shorted together, you are basically going to disrupt the communication between the CPU and the flash. And if they haven't checked their failure paths properly, if you do that right when the bootloader is copying the kernel from flash to memory, it will freak out and say, oh no, I can't read the kernel, whatever, fail. And then it will just drop you to a shell on U-boot, which is like an open source bootloader. This only works for Linux devices, but it actually works a surprising amount of the time for devices that might have been secured a little bit better. And the way that you would deter this is physically cut the traces in the PCB on UART or JTAG instead of just disabling it in software. But yeah, I've used this before. It actually works. It's really cool. And I would definitely try to set something like this up like later for a CTF, maybe next semester if we're in person, but who knows. Yeah, so the next thing I will get into is the RGH, which I talked about on the 360 or the Xbox 360. So to understand this at a very basic level, the way the Xbox 360 boots up is actually kind of complicated. So it first loads a bunch of data from the flash chip, which stores memory like that isn't volatile. And it first loads a bunch of that into memory, and it verifies all the components like as it goes through the boot process. And the way that it does this is, I'm pretty sure it's like RSA or like some actually good form of encryption that normally wouldn't be super feasible to break. But what people were able to do here is they found this thing called the PLL, which for people that haven't done embedded work before, basically that's a way to control the clock speed of the device. And they were able to slow it down a ton so that you might say, well, why does that matter that it's running slower? Well, if you have something running at a slower speed, it's a lot easier to glitch out and confuse with less precision, which is super important to get this stuff working reliably. And that's where the reset glitch hack comes in. So when it's verifying the kernel, right, what that essentially would boil down to in assembly instructions is, run all these RSA encryptions, whatever, and then branch if this register is not 0, or if this register is 0, if it's a successfully verified kernel or not, branch if it's 0. Well, they found out that they were able to slow the clock down and then pulse the CPU reset pin. It would actually erase register values without erasing other register values, so that it would continue booting even though the register that it may have been comparing just got erased to 0 within like a precision like instruction cycle of like 1 or 2 instructions. All of a sudden this register got erased physically by the hardware, and from that they were able to get unsigned code execution, which is actually super cool that they were able to make this work. I'm looking in the chat. I think we might have, let me check here. Oh, cool. Okay. So the next one is the Twiizers attack, which is what was used on the Wii to get a memory dump of the console and revealed a lot of secrets about it. So the way that the Wii worked, this exploit worked, is that the GameCube mode on the Wii is not secure at all. In fact, the GameCube was never really secure. It would just like load unsigned code or was easily broken, but it didn't really matter. They tried attacking the Wii from the GameCube mode, but found out that in this mode, since the Wii has more memory than the GameCube, it restricted them to 16 megabytes of RAM. And that was cool and everything, but they wanted to access the full potential of the Wii. So they devised a plan to get a memory dump so they could at least have something to work on, which is like decrypted and code that they could reverse. But the confusing thing about the Wii is that it actually had 2 processors in it. So one processor called Broadway was like the actual CPU that does like the Wii computations and stuff. But inside of that chip, they had another processor that was actually ARM-based that would run all of their security operations. And that is where like secrets are being stored. But the kicker here is that they all use the same memory. So if you're able to get a memory dump, then maybe those secrets were being stored somewhere. Now, the thing is they tried to do this with the GameCube mode, but they couldn't access that part of the memory because they didn't need to, because they were in GameCube mode and Nintendo had thought of that. But what Nintendo didn't think about is what happens if they glitch out like the memory chip lines and basically, whenever you're getting data from flash or memory, you need to tell it which data you want. And it does that with address lines. And that is like specifying which data you want. And everything has a unique address that is stored so that you can load it back. And basically, they were able to tell the console would make a request to some address line that's in the GameCube space. However, they were able to glitch it so that if they pulled some of these to ground, it would change numbers in these address lines, and that would mean that the Wii would read back memory that was not actually what they had requested, because they're literally changing it with tweezers on the board. It's super cool. And what eventually they were able to do is trick the Wii into reading the wrong 16 megabytes of memory each time. I think it had like 64 megabytes of memory. So they would first read out the GameCube one, then they would glitch it and then read another 16 megabytes and then just keep doing that. And then they were able to get a full memory dump of the Wii and like found a bunch of cryptographic secrets and all this other cool stuff. But yeah, that was pretty much how the Wii worked. So the next one I'm going to talk about is like memory attacks, and what these entail is like, let's say you do have access to system memory. It's generally game over because you can just patch the kernel, disable passwords, do whatever you want, unless it's encrypted or there's some sort of like things to stop this from being an issue put in place, like protections. For OS X and Windows specifically, there is some increased protection. Like I think some of the authentication stuff has been moved to, encrypted, virtualized, like other co-processors or something. But generally, if you get access to memory, it's bad. And this is more of a personal computing problem. Oh, there we go. But the thing is if you're worried, if your attack model includes someone going to your house and physically changing your memory, that doesn't actually make a lot of sense. That's outside of most people's threat model, because then at that point, a burglar could just steal your computer, right? But the thing is this is actually could be an issue on laptops that use that are like left places that may have disk encryption or something. And yeah, but so to solve this, we say, how do we write to system memory without access to the OS? And this is DMA, which I talked about earlier. And a lot of peripherals need DMA to function because they need fast memory transfers. And PCI Express is one of these things. And recently, or at least like in 2013 or 2014, maybe before that, Apple and Intel had worked together on this standard called Thunderbolt, which is PCI Express on a laptop in a cable that you can do whatever you want with, basically. So originally, there was actually not a lot of security, and you could just plug a Thunderbolt device in and get DMA access on the computer, which is really bad. But now there's this thing called security mode, and that will only let you, like, you have to authorize devices to be able to do DMA transfers, which is like, if you get a graphics card and plug it into your laptop, you have to click like allow this device or something. That's all that is. And it turns out, though, that you can actually write Thunderbolt firmware with SPI flash. It's held in SPI flash, which means that you can just patch out the security checks because that chip is like low power and there's not a lot of verification being done. So if you have access to the Thunderbolt controller, you can just erase the memory and put like bad stuff in it. And the reason that this is like an actual attack surface to think about is full disk encryption. So a lot of people trust full disk encryption to keep their files encrypted when the data is at rest, but you can't have it encrypted all the time because then you can't use it. And that's how full disk encryption works, is once your computer's unlocked, nothing's encrypted anymore. So the other thing to note here is that when you put your laptop to sleep, it doesn't re-encrypt anything. Like power is still being sent to all the components. Nothing has been re-encrypted. So like when you unlock your laptop and you're just typing in the password, that's just the Windows authentication thing asking for your password. That's not like disk encryption that you're dealing with. And this attack is called dubbed ThunderSpy, but some clever people found out that if you erase these Thunderbolt security modes, then you plug in a malicious Thunderbolt device, you can just bypass login screens for everything. So if someone didn't properly shut their computer off, you can then access encrypted data without any serious issue. And this was dubbed ThunderSpy. And it's cool because that spy programmer thing that I was talking about that takes like 5 minutes and requires like a screwdriver and like some pre-built tools. So it's not hard to pull off. But yeah, this is a uh, super interesting and pretty novel technique that was like released in August this year. It's really interesting. But yeah, so with that, I have finished my presentation, so I will open it up to questions.